Okay, so for the first average value of a function example, I want to go back to this velocity example we were working with earlier. Let's say we want to find the average velocity on the interval from 0 to 3 seconds. Okay, average velocity is a completely reasonable idea, but the velocity is changing continuously over time. This object is speeding up and slowing down, right? It's moving forwards, it's moving backwards. So to find the actual average velocity on a given interval, what we need to do is use an integral. So the v average on the interval 0 to 3 is going to be 1 over 3 minus 0, the length, 1 divided by the length of the interval, and then times the integral from 0 to 3 of our velocity function, v of t, dt. So what this means is that essentially average velocity is going to be the integral, which is displacement, right? The displacement on from 0 to 3 seconds, and then divided by 3 minus 0, which is just the length of this time interval. So displacement divided by time. Okay, so take that into consideration. The average velocity on an interval is just a formula for displacement, which would be the integral here, divided by the amount of time that has passed, which is just the length of the interval that we're integrating over. This makes total sense, right? Because this is just change in position divided by change in time. This is literally the formula for the slope of a secant line, right? This is the average rate of change formula you learned back in like college algebra, or even possibly, algebra 2 in high school. This is a pretty common formula you learn in algebra class, and I just want to make this connection, right? Displacement is calculated with an integral, and then change in time is the length of the interval that you're integrating over. So we already did this calculation earlier in a previous video. We calculated the integral for the displacement and got negative 4.5. So we're taking negative 4.5 and dividing by 3, and this gives us our average velocity of negative 1.5 meter per second, like that. Okay, so there we go. That's the first example. So the next example I want to look at is the average value of a function, sine of x, on an interval, let's say 0 to pi. So thinking about the sine function here, 0 to pi would be this interval. So the question is, what's the average value of the sine function on that interval? What height is like the average y coordinate for the points on that graph? All right, well, we can figure that out by taking 1 divided by the length of the interval, pi minus 0. I started at 0 again, so I'm doing nice, easy intervals here. And then we're going to take the integral from 0 to pi of sine of x. I think that's an integral we've already done in a previous video, but I will do it again because you probably forgot. We're going to take 1 over pi times the antiderivative of sine, which is negative cosine of x, and then evaluate it at pi and evaluate it at 0, and then we're going to take a difference. So this would be 1 over pi times negative cosine of pi minus negative cosine of 0. And I put that minus negative, I changed that to a plus. So overall here we have 1 over pi times, cosine of pi is negative 1, right? So negative 1. And then plus cosine of 0, which is 1. So we have positive 1 plus another 1. This overall ends up being 2 over pi, which is approximately 0.64. That's the average value of the sine function on the interval from 0 to pi. I bet you can guess. Okay, so that's the average value of the sine function on that interval. I bet you can guess what the average value of the sine function will be on the interval from 0 to 2 pi, right? Because if we average out at 0.64 here, of the next interval, when it's reflected underneath, we're going to average out at negative 0.64. So the average on the whole interval should be the average of those two things, and we would get this entire. We get the entire integral divided by 2 pi, which is 0. It's going to be 0. All right. Okay, so I just wanted to point that out to relate this back to the same thing we discussed in a previous video. Okay, so this is interesting. This is interesting because it is slightly different from how do I want to say this? Okay, so as I was preparing this video, I was thinking about the fact that sine of x relates to the y-coordinate of a point on the unit circle, right? So we're talking about like the upper half of the unit circle here. And And on the upper half of the unit circle, the average value of the sine function should be something like the average value of the y coordinates, right? The y coordinates on this unit circle here, these y coordinates here, right? The average value of sine of x is like saying, as you move along this upper half of the unit circle, what's the average y coordinate? And so as I was preparing this video, I thought to myself, we should be able to calculate that with a different integral. And so now I'm going to dive into something weird that is optional, and if you want to stop watching, because if you don't want to get confused, you can, if you'd like, stop watching and move on to the next video. But if you want to see something really weird and interesting, and which kind of actually relates to something you study later in Calculus 3, then keep watching, because I think this is fascinating and bizarre. Okay, so you've got this idea of calculating the average value of sine of x, right? And that should be somehow related to this idea of the average y coordinate on the upper half of the unit circle. Now, the upper half of the unit circle can be described as a function by y equals the square root of 1 minus x squared, like this. So the average y coordinate on the upper half of the unit circle, perhaps we could calculate that as since this goes from -1 to 1, we take 1 over 2 units, the length of that interval is 2 units, and then times the integral from -1 to 1 of this function which describes the upper half circle, square root of 1 minus x squared dx. Now this integral is one that you will not learn how to do until Calc 2. This is definitely a Calc 2 integral. But you will find, and you can ask Wolfram Alpha in the meantime, before you learn how to do this integral by hand, you can ask Wolfram Alpha, and this is equal to, where's my notes? Oh, it's approximately 0.7 something. Shoot, I didn't write it down. It's 0.74 or something like that. The point is, it's not the same as this. It's not the same as the average value of sine on the interval from 0 to pi. And when I discovered this, as just literally an hour ago when I was preparing my lesson today, I thought that doesn't make any sense. Why would it be different? Because the sine function tells us the y coordinates. That's what it correlates to, right? And so and then the 0 to pi interval is the same as the -1 to 1 interval, right? As the angle ranges from 0 to pi here, on this, the x coordinates will range from -1 to 1. So here's your angle ranging from 0 to pi, and the x coordinates range from 1 to -1, or -1 back to 1 again. It shouldn't matter if you swap the order here, because we're looking at a different function. It should be the same, right? But it's not. And the reason it's not the same has to do with how fast you move along the circle. So if theta changes at a constant rate, then you're going to start and you're going to move at a constant rate along this circle. Okay, then we're also going to have a constant linear speed along the circle. Okay, so that is going to give us one average value. Now, on the other hand, if x changes at a constant rate, you're going to have your x changing at a constant rate along here, right? And then you're going to end up with a quite differing rates of change, where you're going to be moving fast on the sides and you're going to be moving slow on top. Okay? So that means that if in this situation, when you're moving fast on the sides and slow on the top, then as you take your sample points, remember this idea of sampling the different y coordinates, right? Sampling the value of the function at regular intervals. Well, the regular intervals are different, right? In this case, the regular intervals are regular x intervals, right? We're splitting x into regular intervals, and that has a different impact on the sampling, right? We're gonna sample more points up on top here. We're gonna have like points close together, and then on the sides we're gonna have points farther apart, right? So we're going to be weighting the values at the top of the circle higher, right? Because the sampled points are kind of more dense. There are more of them because we're moving slower across the top. And so that's why when we calculated the average value, we tried to calculate the average value using this formula. We got a larger number, right? This with the sine function going at a constant linear speed along the circle, we got 0.64. But with this square root function, with going slower on top, we got 0.7 something. I can't remember that number. But anyway, it's bigger, right? And that's what blew my mind. And I realized that what this means is basically the way that you traverse the upper half circle changes the calculated average value. It's not really like the calculation you do is not inherent to the shape of the curve itself, but rather how you move along it. And you have to decide, what are you going to hold constant? Which variable is changing at a constant rate? Is it the angle which is changing at a constant rate, or the x-coordinate which is changing at a constant rate? And the resulting average value is different. So in Calculus 3, you talk about parameterizing a curve. And you may remember, different ways to parameterizations. If you probably learned about this in College Algebra 2, like the trig class. You talk about how to parameterize curves. If you parameterize a circle, one way you can do that is with x equals cosine of t and y equals sine of t. That's going to give you the first version here. If you parameterize a circle like that, and you try to calculate the average value of the y coordinates across this curve using this parameterization, you will get the 0.64 answer. But on the other hand, if you use a different parameterization where you have x equal t and y equal the square root of 1 minus t squared, right? Then that alternate parameterization for the top of the circle is going to give you this version. And that would give you the 0.7 answer. So what this means is that the way in which you parameterize a circle changes the calculated average value of the function on that circle. And that I had not realized that. I had thought it was going to be independent of parameterization, but it's not. It's not. And that, to me, kind of blew my mind in the last hour. So yeah, I don't know. So there's a little bit of random cool stuff that kind of digs a little deeper into this subject than you really need to go for Calculus 1. Right now for Calculus 1, I think this is not this is not something we really need to wrap our heads around for now. But it's always fun to dig a little deeper and think about things from different perspectives. And this idea of parameterizing curves in different ways is going to be a huge important idea you need to use in multivariable calculus when you start doing things in multiple dimensions and talking about applications for space curves and surfaces and all that kind of thing. Generally, in multivariable calculus, I advise students against using this parameterization. And for most of our applications, when you want to parameterize a circle, it's a lot easier and better to use the cosine and sine parameterization. But every now and then, this is one we need to use, and when we do, it makes a difference. It can produce different results.